Good morning, viewers. This is Kasturi Day. Today I'm back with this chapter that is laws of motion according to ICSE syllabus class 9. Okay, so in this video, I will start discussing the second law of Newton, that is Newton's second law of motion. Okay, so before I start, I will request you to please to subscribe my channel if you have not subscribed yet, and please do ring the notification bell because that will notify you as soon as a new video is uploaded. Okay, and if you are liking the videos, press the like button, share with your friends so that they can also be benefited from these videos. And if you if you are starting your day, that is when you are starting your day, please do meditate and then you start your day, because that will increase your concentration, increase your interest in your studies, and to become successful. Okay, so let us meditate for 1 minute and then we start with the discussion. Okay, so for meditation, please concentrate to the point of light. Think that light is coming with you and that is giving you energy. The whole body of yours is being energized, lightened up. You are getting energy, and that energy is being circulated in the whole room when you are meditating. You're getting interest in whatever you are doing. You're happy in what you're doing. You're enjoying with what you're doing. And thus you are becoming successful. At the end of today, you are thanking God for the whole day you have spent. Okay? That's all the meditation for today. Okay, so let's back to our discussion. Okay. So for the day, we'll start with the other examples of law of inertia. That's the first law, which you will be discussed in my, in the last video, which I've discussed, where the law of inertia stated that the body is in the state of rest or in a uniform motion, in a state of uniform motion with a velocity, with a constant velocity. Okay, so that is the law of inertia, or the Newton's first law of motion. Okay, so we have also discussed the examples of, there are three types of inertia, that is inertia of rest, motion, and direction. We have discussed some examples also, but some other examples are still there. These will help you in solving your question answers. So let me discuss some of them. Okay, so first we come to inertia of rest. See, when we shake the branches of a tree, the fruit falls down. Why it is so? Because when you are shaking the branches of the tree comes in the motion. The leaves, the branches, they come in the state of motion, but the fruits have still not come in motion. Okay, so then what will happen when you are shaking the branches, the branches of the tree that will come in motion, and the fruits which are not still in motion, they, as their their stalk has become, the fruits have become ripe, and their stalks are old enough, so they will, due to their, and due to the gravitational force, they will come down. Okay, as they are old enough, they will get plucked from the branches of the tree, and they will come down with due to the gravitational force and fall down on the earth. Okay, then in the next picture, you can see, on striking the coin at the bottom of a pile of carom coins with a striker, lowest coin only moves away while the rest of the pile remains intact. What happens when you stack up the coins in one pile, carom coins in one pile, and you are hitting the striker? the lowest coin will only move. The other will remain as it is and the pile will remain intact. Why doesn't it fall? Because what happens, these, when you are hitting the striker and it hits the bottom coin comes in motion. Okay, the bottom coin comes in motion, and with that motion, it will move out. But the upper part of the pile, leaving the bottom one, that is still in not, that pile is not still in motion, that is still in the rest position. That's why, due to the gravitational force, it will just come down, and it will, the whole stack will be, the whole pile will remain intact. Okay, it will not, it will come down due to the gravitational force, but it will remain intact due to the inertia of rest. Okay, then next is the example of this one. See, a glass is there, a smooth card which is placed over the mouth of a tumbler in a flicked sharply and is flicked sharply in the horizontal direction. The card flies away, but the coin kept over the card falls into the glass. Why it happens like this? Because why it does not fly away with the card? Because what happens when you are striking the card? Okay, when you are striking the card comes in motion, but the coin which is over the card, that is still not in motion, that is in the state of rest. Okay, and so that coin is, as there is no support below, and there is a gravitational force there that will pull the coin down. Where it is down, it is coming down inside the glass, as there is a glass just below the coin. Okay, so it will fall inside the glass. So this is also an example of law of inertia. Okay, next we come to inertia of motion. So what do we see? First is a cyclist who is riding along a level road does not come to the rest immediately after the stop paddling. Okay, so what happens when a cyclist uh, is riding a cycle? He paddles on. Okay, but when he wants to come to rest, okay, when he wants to stop his cycle, he will stop paddling, but the cycle will not immediately come to rest. Why? Because when he has stopped paddling, the cycle initially was in the state of motion and in uniform velocity, constant velocity rather. It was in constant velocity, and that cycle was in motion, and when he has stopped paddling, immediately it will not stop to rest. So the cycle will move on a little bit, and then after some time it will stop paddling. I mean it will come to rest. Okay. Next, a person jumps out of a moving car train, he will fall down. Why? When a person is jumping out of a moving train, initially the train was moving, so his lower part, the person's lower part of the body will remain in the state of motion along with the train. But when he jumps out of the train, the the whole body of his was in the state of motion. Okay, but when he jumps out of this train, the lower part of his body will come to rest, but his upper part was still in motion. So that's why he falls down. Okay. So this is the picture. He's jumping out and then he is falling down. Okay. Next, an athlete often runs before taking a long jump. What? Why? Because when the athlete is running, he will keep his whole body in a state of motion. Okay, and when he is taking a long jump, that will help him easily to jump further. That will help him to fly out further. Okay, so that's why he keeps makes a he runs a little bit and then he starts jumping. Take a long jump. So this is also an example of this one, law of motion. inertia of motion. Okay. Now we come to the second law of motion, that is for second law of motion. First we come to the linear momentum, then the change in momentum of the body. Okay. So, what is first? Let me say, what is first? The second law of motion states. It states that the acceleration produced by a moving body is directly proportional to the force applied over it and is inversely proportional to the mass of the object. Okay. So, the acceleration which is produced by a moving body, the acceleration which is produced by moving body is directly proportional to the force applied over it. That means if the acceleration increases, the force will also increase, or the rather force is increased, the acceleration will increase. Okay, and it's inversely proportional to the mass of the object. That means if the mass increases, the force will decrease, and if the mass decreases, the force will increase. Okay. Sorry, the acceleration will increase. Okay. So if acceleration increases, the mass is less, and if the acceleration is less, then the mass will be more. So the acceleration is directly proportional to the force, and acceleration is inversely proportional to the mass. Okay. So this is the rate of change of momentum of the body is directly proportional to the force applied of it, and the change in momentum takes place in the direction in which the force is applied. Okay, so Newton's second law of motion states that the rate of change of momentum, it is directly proportional to the force applied on it, and this change in momentum takes place in the direction of the force applied. Okay. So for this, let us first come to linear momentum. What is linear momentum? What is change in momentum? First is linear momentum. What is linear momentum? It's the force which is needed to stop a moving body. Linear momentum, it's the force which is used to stop a moving body in a definite time. It's the force that is needed to stop the moving body in a definite time, and which depends both on the mass of the body and its velocity. Okay. So linear momentum is nothing but it's a force which is applied on a moving body in a given time. Okay, and this depends on mass and the velocity. The value is given by the product mv, that is mass and the velocity. So product of mv, which is also known as linear momentum, or p, small p. Okay, so p, small p is equal to small m into small p. Since SI unit of linear momentum is kg meter per second, or CGS unit is gram centimeter per second. Okay, kg meter per second or gram centimeter per second. Okay, so change in momentum of a body is defined as the change in the product of the mass and the velocity of the body. So linear momentum is mass into velocity, and change in momentum will be the change in the product of the mass and velocity. Okay, it is given as change in momentum is equal to delta P is equal to delta mv. Change is the product can be due to the either in the change of either the change in mass or the change in velocity, or both. So as this linear momentum depends on mass and velocity, therefore the change can be change in momentum can be can be due to either change in mass, either change in velocity, or both, or change in mass and velocity both. Okay? So next will be the rate of change of momentum of a body is equal to the product of the mass of an object and the acceleration produced in it due to the force acting on the body, provided that the mass of the object remains constant. So rate of change of momentum. First we did change of momentum. First is linear momentum, change of momentum, and now we come to rate of change of momentum. that is equal to the product of mass of an object and acceleration which is produced due to the force applied on it. And provided there's one condition between, under this one is that mass of the object should remain constant. For example, see rate of it is mathematically represented like this: rate of change of momentum is equal to mass into acceleration. So therefore, it will be delta P by delta T is equal to M into A. Okay? Delta T means within time. So rate of change of momentum means change of momentum by time, change in time, and that will be equal to mass into acceleration. And acceleration, we know that it's velocity into time. I'm sorry, acceleration will be equal to initial velocity, final velocity minus initial velocity by time. So acceleration into time will be equal to velocity. Okay, acceleration into time will be equal to velocity. So we know that mass into velocity gives the change in momentum. But if in case of velocity, in place of velocity, if we write acceleration into time, that is also okay. Now, as it is rate of change of momentum, so change of momentum, change of momentum by change of time will be equal to mass into acceleration. Clear? Next is we come to the rate of change of momentum of the body is directly proportional to the force applied to it, and the change in momentum takes place in the direction in which the force is applied. For a constant mass, see, we told you that the rate of change of momentum of a body is directly proportional to the force applied on it, and the change in momentum takes place in the direction of the force applied. So for a constant mass, when the mass remains constant, force equals to mass times acceleration. That means mass into acceleration. Okay, when the mass is constant, therefore force will be equal to mass into acceleration. Mathematically, Newton's second law will represent that. Let mass be m, initial velocity be u, final velocity be v. Okay, therefore momentum will be mass into velocity. Therefore, initial momentum will be mu and final velocity will be mv. Therefore, change in momentum will be mv minus mu. Okay. Now, from the picture, we can see this. So, rate of change of momentum will be mv minus mu. This will be mu by t. Okay. So, that means what? Force is directly proportional to rate of change of momentum according to Newton's second law. Okay. So, therefore, force is directly proportional to mv minus mu by t, or you can say it's directly proportional to m within brackets v minus u by t. That is v minus u by t is, we know it's acceleration. Okay. So using the above relation, we get what? In place of v minus u by t, we can write a. So F is directly proportional to ma. Okay. And this directly proportional is we make if it is made a constant proportion, that is we represent it with k. Okay, so where k is proportionally constant, we make F is equal to kma. Okay, now 1 unit force is defined as the force applied at the object of mass 1 kg to produce an acceleration of 1 meter per second. So 1 unit force will be equal to k into 1 kg into 1 meter per second square. Okay. So the 1 unit force, that means 1F is equal to k, as k is constant. So k into 1 kg into 1 meter per second square. So it's a unit of acceleration, then mass. Here its force is 1 unit force. Okay. So this is the second law derivation, how F is equal to kma, how it is derived. Okay. So if k is equal to 1, then okay. So if k is equal to 1, by putting the value k is equal to 1, because we found that f is 1, m is 1, a is 1, but if k is 1, then what happens? F equal to ma. Okay, therefore the derivation is like this: force is equal to mass into acceleration, where k is equal to 1. Okay, the unit of mass is kg and the unit of acceleration is meter per second square. Okay, if force, mass and acceleration is taken as 1 unit, therefore 1 Newton force is equal to 1 kg into 1 meter per second square. Or you can say Newton N is equal to kg per meter, kg into meter per second square. Or you can say equation can also be written as A is equal to F by M. As F is equal to MA, M into A, therefore it can be said that A is equal to F by M. Okay, so according to this equation, Newton's second law can also be stated that acceleration produced by the moving body is directly proportional to the force applied over it and inversely proportional to the mass of the object. So from the relation, we can say that acceleration increases with the increase in force and vice versa. That is, if the force increases, the acceleration increases, or if the acceleration decreases, the force will decrease also, as it is directly proportional. And acceleration decreases with the increase in mass and vice versa. That is, acceleration increases, mass will decrease. So a small vehicle requires less force. Small vehicle, it requires less force because the vehicle is small, the force will be less to attain more acceleration than a heavy vehicle to get the same acceleration. Okay, so small vehicle, mass is less, so acceleration will be more and the force will also be less. Heavy vehicle, mass will be large, so acceleration will be same or less, you can say, but the force will also be large. Now, according to Newton's second law of motion, the acceleration produced in a body of a given mass is directly proportional to the applied force. That is, A is directly proportional to F when mass remains constant. When mass remains constant, A is directly proportional to F. That means A increases, F increases. Mass remaining constant. Like this, the curve will be straight line passing through the origin. Like this, it will be, okay? Near the origin, not passing through the origin, but near to the origin, okay? So that when acceleration increases, force will increase. Next is, according to the second law, Newton's second law of motion, the force needs to produce a given acceleration in the body is directly proportional to the mass of the body. It's not directly proportional. The force needs to produce a given acceleration in the body is, okay, so a force is directly proportional to mass where acceleration remains constant. Here it was in the previous, acceleration is directly proportional to force where mass is constant. In the second case, force is directly proportional to mass where acceleration is constant. That means force will increase, mass is also increase. That means heavier vehicles, more force. Less heavy vehicles, force will be less. Okay. Then combining both A and B, that is F is directly proportional to mass and A is directly proportional to F. So F is directly proportional to M into A. That means F is equal to KMA, where K is constant. The unit of force is so chosen that K is equal to 1. Then when M is equal to 1 and A is equal to 1, then M is 1, A is 1, then K also becomes 1. Unit force also. Force is also 1, then K also 1. Constant. K is constant. So the amount of force is taken as 1 unit force, which when applied on a body of unit mass produces a unit acceleration in the body. So mathematically we can say F is equal to M into A, or force is equal to mass into acceleration. This is on the basis of this experiment it has been concluded. Okay. Now, if if in a given force, if a given force is applied on the bodies of different masses, okay, masses are different, then the acceleration produced in them will be inversely proportional to their masses. Okay, that means A is inversely proportional to M for a given force, and mass is different. So acceleration will be inversely proportional to mass, and the graph will be a hyperbola. Okay. Now we come to the units of force, CGS and SI unit. CGS unit is dyne, SI unit is Newton. So what is the relation between dyne and Newton? 1 Newton is equal to 1 kg into 1 meter per second square. We know that. So 1 kg is converted to grams, that is 1000 grams, and 1 meter per second square is 100 centimeter per second square. Okay, so we can write 3 and 2, 5. So 10 to the power 5 grams per centimeter, sorry, grams centimeter per second square. Or you can say 10 to the power 5 dyne. So the 1 dyne is equal to 1 gram into centimeter per second square. Or you can say 10 to the power 5 dyne is equal to 1 Newton. So 1 Newton is equal to 10 to the power 5 dyne. Now we come to some examples of Newton's second law of motion. So first is a fielder. We have seen in the field that when catching a ball, when a fielder is catching a ball, he will pull his hand backwards. Why? It's because while catching a cricket ball, the momentum of the ball is reduced to 0. Otherwise, it will hurt his hand. So the momentum is made, which of the ball is made to 0. If the ball is stopped suddenly, its momentum will be reduced to 0 instantly. It has to become 0 when it is stopping the ball. So velocity will become 0, then its momentum will automatically become 0. But if he stops it instantly, okay, like this, if he just catches it without pulling his hand backwards. So what happens? Instantly the ball is getting stopped. So that time the momentum will instantly become 0, which will cause the instant rate of change in momentum, due to which the ball will exert great force on his hand, on the player, on the player's hand, due to which the player's hand may get hurt, may get injured. So by pulling his hand backward, uh, he gets more time to change the momentum to become 0, so that his hand does not get hurt. He gets more time while he's pulling his hand backward. He's getting more time to change the momentum into 0. Okay, so how it is mathematically derived, let us find out. Okay, so if u is the initial velocity of the ball and m is the mass of the ball, when it reaches the hand of the player and it catches it, the initial momentum of the ball will be mu. Now when the cricketer stops the ball, so initial momentum, it was coming to the player, it is mu. Now, when he's stopping the ball, its velocity v becomes 0. Final velocity becomes 0. So, final momentum will be m into 0. That means 0. So, momentum is becoming 0. So, change in momentum will be final minus initial. That will be equal to 0 minus mu, or you can say minus mu or mu numerically. Why it is negative sign? Because the negative sign shows that the change in momentum is in the opposite direction to the initial direction of motion. Okay, so change in momentum will be in the opposite direction. So that's why it's a negative sign. Now, if the cricketer catches the ball without withdrawing the hand backward, the time taken by the cricketer is much less. So let us consider it to be T1. Now, the force applied by the ball on the hands of the cricketer is F is equal to change in momentum by time. That is change in momentum. Initially, it was mu. So, mu by T1 will be the force which is applied by the ball on the hands of the cricketer if he catches the ball like that without withdrawing his hand. Okay. Now, when the cricketer catches the ball by withdrawing his hand, he takes much longer time. That is, say, T2. Okay, and then the force applied by the ball on the hands of the cricketer will be mu by T2. Now, as we know that he is getting more time when he is pulling his hand backward, so T2 will be more than T1 and F2 will be less than F1 because when he is pulling his hand backward, he is getting less force on his hand. So F2 will be less than F1, or the force exerted by the ball is much less when he is withdrawing his hand backward. So the cricketer avoids the chances of getting injured to his palms by withdrawing his hands. Clear how this is done? Okay, this happens. The next, another example is an athlete when he's taking a long or high jump. He is landing or he is landing on a cushion bed or a sand bed. Okay, why? Because when an athlete falls on the ground by performing a high or a long jump, the momentum of his body will become zero. So if he falls just like that, so instantly his momentum will become zero. That will create a large force and his body may get hurt. Okay, it is instantly falling on the ground. Okay, but when there is a cushion bed or sand is there, then his momentum will get more time to become to zero. That is to be reduced to zero. Delayed. His time will be delayed. So less force will act on his body, which will prevent the athlete from getting hurt. Same theory in the first one, which was discussed like that only. Next is, excuse me, seat belt in a car are provided to prevent the passenger from getting thrown in the direction of the motion. In case of sudden brake or any accident, passengers may get thrown in the direction of the motion of the vehicle and may get fatal injuries. But the stretchable belts, seat belts, prevent the passenger body to fall suddenly and thus increasing the time of the rate of momentum to become to zero, which will reduce the effective force, preventing the passenger from getting any fatal injuries. Same thing, same process. That is when a passenger is traveling in a car, okay, so suddenly his car stops by either he is applying a brake, sudden brake, or any accident is there. So he will not come forward. Why? And not get any injury. Fatal injury will not be, it can be avoided. Why? Because when he is in motion, his body is in motion. Okay. But when he is just applying the weight instantly or by any accident, his car is being stopped, then what happens? His lower part of the body will get stopped, his upper part is still moving. So if there's a tendency of of his body to come forward and getting the injury. Okay. So the seat belts are applied. We know that. Okay. And when the seat belts is applied, the body gets more time to change the rate of momentum to become zero, to reduce to zero, which will prevent the passenger from getting any fatal injury. And if there was no seat belt, then the passenger would just hit on the front seat or he will fall forward. Okay, and instantly, if it stops, then he will instantly get hurt. Okay. So this is the prevention. Now, another example is we have seen that a glass tumbler or a glass, any glass ball or any glass item, if it falls on the floor, directly on the floor, it will break. But if it falls on a carpet, on a sand, okay, then it will not break. Why? Again, the same theory. That is, when it directly falls on the floor, its momentum, change of momentum will instantly get into zero, get to reduce to zero, and it will break, get hurt. The force will be more and the glass item will break, glass vessel will break. But if it falls on the carpet, then what happens? a less force will be applied because it will get time to change the rate of momentum to get to zero. That's why the vessel will not break. Okay. So this much for today. So please go through this. If you have any doubt, please do write in the comment box. Do share with your friends so that they can also be benefited from these videos. And if you are liking the videos, press the like button. And if you have not subscribed yet, please do subscribe. Okay. And ring the notification bell because this will notify you as soon as a new video is uploaded. Okay. And please do meditate before you start your day. Okay. So thank you for joining and have a good day.